This video is Lab 2 for Physics 2211, Section N on the motion of a falling object. In this lab, I'll observe a crumpled up paper ball fall from rest, moving in the negative y direction. We will then predict the motion of the falling object with a computational model with only the force of gravity, and a model with both the force of gravity and the force of drag. Newton's second law can explain the forces acting on the paper ball, which will result in an acceleration, or a non-constant velocity, which causes the net force to not equal zero. In the drag model, I will represent the force of drag to be proportional to the velocity squared, which is represented by a constant b times the velocity squared. After recording the video, I observed it in Tracker, setting the origin at the ground and measuring the ball's position at each time frame. From Tracker, I've recorded all my observed positions and have a time set of 0.033 seconds, which runs until 0.667 seconds, which ends at frame 80. In GlowScript, I've created two computational models to predict the position of my falling object. In both models, I set the mass to 0.0045 kilograms, the initial position to the vector 0, 1.830 meters, the initial velocity to the vector 0, 0 meters per second, the time step to 1/30th of a second, and the while loop to run until 2/3 of a second. In the loop, the velocity updates by adding the net force divided by the ball's mass times the change in time, and the position updates by adding the velocity times the change in time. The arrow scale in both models is set to 20. For the no drag model in the loop, the weight force equals the ball's mass times negative g times the j hat, and the net force equals the weight force. Arrow 1 is set to the ball's position, with its axis being the weight force times the arrow scale. Here is the resulted graph and ball's free body diagram after the code is run. For the drag model in the loop, the weight force is the same, but we now add the drag force, which is b times the magnitude of the ball's velocity squared times j hat, with b equaling 0.00196 and having the net force equal the weight force plus the drag force. Arrow 1 and arrow 2 are both set at the ball's position, with arrow 1's axis being the weight force times the arrow scale, and arrow 2's axis being the drag force times the arrow scale. Here is the resulted graph and ball's free body diagram after the code is run. After creating the models, I entered all the predicted data and observed data into a spreadsheet and graphed it to compare all the positions. Blue represents the observed position, orange is the predicted position without drag, and red is the predicted position with drag. The observed and predicted position with drag align almost exactly, with a little discrepancy around the time of 0.4 seconds, which I will assume was caused by human error measuring the observed position in Tracker. As for the predicted position without drag's data, it fits the other two position data values well at the beginning, but its position will change more exponentially since it only has a force of gravity, meaning the speed will increase more over time compared to the other two models. Additionally, this model without drag doesn't fit observed position data well because there wasn't only the weight force acting on the paper ball, and it will experience some drag as it falls, meaning we cannot assume it is only affected by the force of gravity or the weight force. After analyzing the data, we need to discuss the terminal velocity, which is the constant speed reached of a free-falling object when resistance force prevents further acceleration. First, did either model predict the terminal velocity? In the computational model, we can graph the velocity versus time. The left shows the no drag velocity graph, and the right is the drag velocity graph. Neither graph clearly shows the terminal velocity, but the drag velocity graph is approaching the terminal velocity, as we can see the graph's curve leveling out to a flat horizontal line. Next, if the falling object was initially thrown downward, would the terminal velocity be the same or different from when it was dropped from rest? For this, I can look again at the two velocity graphs from the model. If the object had an initial velocity, the velocity at time 0 seconds would change, but the terminal velocity would not, because the forces acting on the falling object still have the same magnitude, meaning the terminal velocity will be the same, and the only difference will be that the falling object with an initial velocity will take either a longer or shorter time to reach the terminal velocity, depending on what its initial velocity is. In conclusion, the lab accomplished depicting the effect of the weight force and drag force on a falling object, which will affect the object's position, velocity, and net force. Thank you.